Section 6.5, Quantum Mechanics and Atomic Orbitals. In 1926, the Austrian physicist Edward Schrödinger proposed an equation now known as Schrödinger's wave equation that incorporates both the wave-like behavior and the particle-like behavior of the electron. His work opened a new way of dealing with subatomic particles known as either quantum mechanics or wave mechanics. The application of Schrödinger's equation requires advanced calculus and will not be concerned here with the details of his approach. We will, however, quantitatively consider the results he obtained because they give us a powerful new way to view electronic structure. Let's begin by examining the electronic structure of the simplest atom, hydrogen. In the same way that a plucked guitar string vibrates as a standing wave, Schrödinger treated the electron as a standing circular wave around the nucleus. Just as the plucked guitar string produces a fundamental frequency and a higher overtones or harmonics, there is a lowest energy standing wave and a higher energy ones for an electron in an atom. Solving Schrödinger's equation leads to a series of mathematical functions called wave functions that describe the electron in an atom. These wave functions are usually represented by the symbol psi. Although the wave function itself has no direct physical meaning, the square of the wave function, psi squared, provides information about the electron's location when the electron is in an allowed energy state. For the hydrogen atom, the allowed energies are the same as those predicted by the Bohr model. However, the Bohr model assumes that the electron is in a circular orbit of some particular radius about the nucleus. In the quantum mechanical model, the electron's location cannot be described so simply. According to the uncertainty principle, if we know the momentum of the electron with high accuracy, our simultaneous knowledge of its location is very uncertain. Thus, we cannot hope to specify the exact location of an individual electron around the nucleus. Rather, we must be content with a kind of statistical knowledge. In the quantum mechanical model, we therefore speak of the probability that the electron will be in a certain region of space at a given instant. As it turns out, the square of the wave function at a given point in space represents the probability that the electron will be found at that location. For this reason, psi squared is called the probability density or the electron density. One way of representing the probability of finding the electron in a various region of the atom is shown in Figure 617. Figure 617, Electron Density Distribution. This rendering represents the probability of where in the space surrounding the nucleus the electron is to be found in the hydrogen atom in its ground state. In this figure, the density of the dots represents the probability of finding the electron. The regions with a high density of dots compared to a relatively large values for psi squared and are therefore regions where there is a high probability of finding an electron. In section 6.6, we will say more about the ways in which we can represent electron density. Section 1. Orbitals and quantum numbers. The solution to Schrödinger's equation for the hydrogen atom yields a set of wave functions and corresponding energies. These wave functions are called orbitals. Each orbital describes a specific distribution of electron density in space as given by the orbital's probability density. Each orbital, therefore, has a characteristic energy and shape. For example, the lowest energy orbital in the hydrogen atom has an energy of negative 2.18 times 10 to the negative 18 joules, and the shape illustrated in Figure 617. Note that an orbital, which is a quantum mechanical model, is not the same as an orbit in the Bohr model. The quantum mechanical model does not refer to orbits because the motion of the electrons in an atom cannot be precisely measured or tracked, and that is the Heisenberg uncertainty principle. The Bohr model introduced a single quantum number, n, to describe an orbit. The quantum mechanical model uses three quantum numbers, n, l, and m1, which result naturally from the mathematics used and describe an orbital. Let's consider what information we obtain from each of these quantum numbers and how they're interrelated. Number 1. The principal quantum number, n, can have positive integral values of 1, 2, 3, and so forth. As n increases, the orbital becomes larger and the electron spends more time further from the nucleus. An increase in n also means that the electron has a higher energy and is therefore less tightly bound to the nucleus. For the hydrogen atom, E sub n equals negative 2.18 times 10 to the 18 joules over the principal quantum number, as in the Bohr model. Number 2, the second quantum number, the angular momentum quantum number, L, can have integral numbers from 0 to n minus 1 for each value of n. This quantum number defines the shape of the orbital. We'll consider these shapes in section 6.6. The value for L for a particular orbital is generally designated by the letters S, P, D, and F, corresponding to L values of 0, 1, 2, and 3, respectively, as summarized here. The S subshell has a L value of 0, the P subshell has an L value of 1, D subshell has an L value of 2, F subshell has an L value of 3. Number 3, the magnetic quantum number, M1, can have integral numbers between negative L and positive L, including 0. This quantum number describes the orientation of the orbital in space, as we'll discuss in section 6.6. Notice that because of the value of n can be any positive integer, an infinite number of orbitals for the hydrogen atom is possible. The electron in a hydrogen atom is described by only one of these orbitals at any given time. We say that the electron occupies a certain orbital. The remaining orbitals are unoccupied for that particular state in the hydrogen atom. We'll see that we are mainly interested in the orbitals of the hydrogen atom with small values of n. The collection of orbitals with the same value of n is called an electron shell. All the orbitals that have n equals 3, for example, are said to be in the third shell. Further, the set of orbitals that have the same n and L values are called a subshell. Each subshell is designated by a number, the value of n, and a letter, S, P, D, or F, corresponding to the value of L. For example, the orbital that has n equals 3 and L equals 2 are called 3D orbitals and are in the 3D subshell. Table 6.2 summarizes the possible values of the quantum numbers L and M1 and the values of n through n equals 4. The restrictions on the possible values of the quantum numbers give rise to the following very important observations. Number 1. The shell with principal quantum number n will consist exactly n subshells. Each subshell corresponds to a different allowed value of L from 0 to n equals negative 1. Thus, the first shell, n equals 1, consists of only one subshell, the 1s, L equals 0, and the second shell, n equals 2, consists of two subshells, the 2s, L equals 0, and the 2p, L equals negative 1, or positive 1. The third shell consists of three subshells, 3s, 3p, 3d, and so forth. Each subshell consists of a specific number of orbitals. Each orbital corresponds to a different allowed value of m1. For a given value of L, there are 2L plus 1's allowed values of m1, ranging from negative 1 to positive 1. Thus, each S, L equals 0, subshell consists of one orbital, each P, L equals 1, subshell consists of 3 orbitals, and each D, L equals 2, subshells consist of 5 orbitals, and so forth. A total number of orbitals in a shell is n squared, where n is the principal quantum number of the shell. The resulting number of orbitals for the shell, 1, 4, 9, 16, are related to a pattern seen in the periodic table. We see that the number of elements in the rows of the periodic table, 2, 8, 18, 32, equals twice these numbers. We'll discuss the relationship further in section 6.9. Figure 6.18 shows the relative energies of the hydrogen atom orbitals through n equals 3. Each box represents an orbital. Orbitals of the same subshell, such as the 2p, are grouped together. When the electron occupies the lowest energy level, 1s, the hydrogen atom is said to be in the ground state. When the electron occupies any other orbital, the atom is said to be in an excited state. At ordinary temperatures, essentially all hydrogen atoms are in the ground state. The electron can be excited to a higher energy level by absorption of a photon of appropriate energy.